In 1831, two physicists, Michael Faraday in England and Joseph Henry in America, made a discovery that was to change the world. Both, without knowledge of the other, found that when a magnet was moved into a coil of wire, an electric current was established in the wire. The current was momentary, occurring only when the magnet was in motion. This was astounding, for at that time electric current needed a battery of some sort. Only motion of the magnet was all that was required to produce current. This was electromagnetic induction. Amazing. It was soon discovered that a current produced in a wire was due to a voltage that was induced by motion of the magnet. Electromagnetic induction, the creation of voltage when a magnetic field changes with time. Voltage could be induced by motion of a magnet or motion of the wire relative to the magnet. Only relative motion between magnet and wire was needed. How much induced voltage depended also on the number of coils of wire involved. More coils, more voltage. When Faraday was asked by his queen of what importance was his electromagnetic induction, he replied that she would soon tax it. For Faraday was correct. It became the underbelly of the Industrial Revolution. With ample electricity, motors could be built, factories could house them, and workers would produce goods as never before. Does this mean that electromagnetic induction is an energy source? The answer is no. Work is done to produce relative motion of magnet and coil. Here a coil of one loop for simplicity. The amount of electric energy induced is the same as the work done in producing it. Electricity is a carrier of energy, not a source. This point is often missed in learning about electromagnetic induction. That work may involve steam that drives a turbine, and the steam, after all, needs an energy source to convert water to steam. Or high-speed plasma produces electromagnetic induction without the need of coils or wire. Here the plasma requires an energy source. However produced, an energy source is needed for electromagnetic induction. One way to produce current in a coil of wire is with another coil in which current undergoes a change. Call one coil the primary and the other the secondary. Whenever the primary switch is opened or closed, voltage is induced in the secondary circuit. That's because the magnetic field of the primary that reaches into the secondary undergoes a change. No change, no electromagnetic induction. The electric meter in the secondary indicates the amount of current produced. Or we can wrap both primary and secondary coils about an iron core. This arrangement is an electric transformer. Changes of voltage, and therefore current, in its magnetic field in the primary induce voltage in the secondary. In this way, electric power can be transferred from one coil to the other. And the voltages involved depend on the relative number of turns on each coil. Here we have fewer coils in the secondary. But what if there were more coils in the secondary than the primary? Then the voltage induced in the secondary would be greater than the voltage in the primary. Does this mean a multiplication of energy? A multiplication of power? No way. As the voltage goes up in one coil, the current goes down in the other. Recall, electric power is given by P equals IV. Power equaling IV can mean small current times large voltage, voltage stepped up, or large current times small voltage, voltage stepped down. Like in all areas of physics, the conservation of energy reigns. Here the voltage input is 1 volt, and 1 volt is induced in the secondary. 1 volt is also induced in the added loop. Adding the two loops and the voltage induced in each, we see 2 volts induced in the double loop circuit. Makes sense. Study the details of transformers in your textbook. Here's a photo of one. In about 1860, some 30 years after the discovery of electromagnetic induction, James Clerk Maxwell replaced the notion of voltage with electric and magnetic fields. Maxwell stated that An electric field is induced in any region of space in which a magnetic field is changing with time. And also, a magnetic field is induced in any region of space in which an electric field is changing with time. Electromagnetic waves pass right through one another. The space around you is filled with radio waves, TV signals, mobile phone messages, and light, each doing its own thing while ignoring all the others. How fortunate for us! On the eve of his discovery, story has it that Maxwell had a date with a young woman he was later to marry. While walking in a garden, his date remarked about the beauty and wonder of the stars. Maxwell asked how she would feel to know that she was walking with the only person in the world who knew what starlight really was. For it was true. At that time, James Clerk Maxwell was the only person in the world to know that light of any kind is energy carried in waves of electric and magnetic fields that continually regenerate each other. Because of electromagnetic induction, the energy of elevated rivers has been harnessed, turned to electricity, and transported to distant cities. The advent of motors, generators, and transformers occurred about the time the American Civil War was being fought. From a long view of human history, events such as the American Civil War will pale into provincial insignificance in comparison with the more significant event of the 19th century, the discovery and implementation of the electromagnetic laws. I want to leave you with a question. Between the concepts of voltage and energy, what can a transformer multiply? What can it never multiply? Until next time, good electromagnetic energy.